Welcome to the chemistry class. So last time we talked about the solid, liquid and gases and how they change. Today we are going into the next topic 1.4, heating and cooling curves. So what do I mean by heating curve or cooling curve? What is that? So a heating curve or maybe a cooling curve is basically a graphical representation of changes in a substance, any substance. It could be water, it could be compound, it could be an element, any substance. When it changes physical state, okay, and that physical state would change when you heat it or cool it down, right? So that's a heating curve or cooling curve. Okay, when you are heating it, you call it heating curve or a heating graph. When you are cooling it, that's called a cooling curve or a cooling graph. Okay, so let's try to draw a heating curve first. Heating curve or heating graph for water. Okay, so best example is water. So let's try to draw this. Okay, this is a graph. Okay, so what do we do is that we are going to have on the x-axis we have time. Okay, time increasing from left to right, and on the y-axis we have temperature in degrees Celsius, increasing from bottom to top. Okay, so let's say we have here I don't know, let's say we have okay, so we have this this is minus 25 degrees Celsius, that's 0, and then we have 25, 50, 75, 100 and 125, maybe above that. Okay, 150 and on, right? So that's the graph we are going to use. Okay, let's say here we have time. Okay, so that would be like maybe in minutes, right? 1 minute, right? So let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay, something like that. So what happens is that we know at 0 degree Celsius, okay, oh, we can move this a little bit at the bottom just to make sure you get the idea. Okay, let's keep it here. So I hope you and this is fine. Okay, right. that would be good. So we know that at 0 we have ice, right? This is solid ice at 0. Okay. If you go to temperature below 0, it's 100% solid. That's solid. That's ice. Okay. This is ice. Right? Solid ice. But at 0 degrees Celsius, okay, at the 0 degrees Celsius, you have solid ice, but it starts melting. This is the freezing point of the water, but at the same time, it's also the melting point of water. Okay. So at this point, what's going on is that the temperature at the 0 of the ice or melting ice, the temperature remains constant. It means the temperature would not increase or decrease from 0 degrees Celsius. Okay. This is the melting point of ice, but at the same time, it is the freezing point of water. So at this point, the ice and water would have kind of like an equilibrium. If you keep heating it up, or if this ice keep getting more and more energy, more and more heat, so the equilibrium would shift towards water, all the ice would melt, but the temperature would remain 0 until all the ice have been melted into water. The moment all of it changed into water is the point when the temperature would start rising up again consistently. If you keep heating, the temperature would keep rising up consistently. So at this point, it is liquid. Liquid means water. All right. So temperature is consistently rising up, right? So in this case, what happened? Now here, if you keep heating it, right? Keep heating until ice completely change into or melts into water. Then temperature start rising again. At this point, temperature of water rise up consistently. If you heat consistently, the temperature would keep rising up and up and up. All right. And all that heat energy, all of that heat energy increase kinetic energy of water. Increase Ke means kinetic energy of water. So the more you heat, the more would be the kinetic energy or the movement of water molecules, right? Until it reaches the 100 degrees Celsius. The moment it reaches 100 degrees Celsius, the temperature again become constant. This is 100 degrees Celsius, right? Which is the boiling point of water. At this point, the most of the temperature, like at this point, the temperature become constant. Okay, so what's going on at this point? Temperature again becomes constant it would not increase or decrease. But if you keep heating it, all the heat energy is used up to break any kind of attractive forces between water molecules, so they can escape into the vapors. All right? This is what would happen. You keep heating it, the water molecules would keep escaping after breaking the attractive forces, which is basically hydrogen bonding between them. Okay? But the temperature would remain constant until all the water have been transformed into vapors. All the water has been evaporated. The moment all the water has been evaporated into the gaseous state, so at this state, water is boiling. Okay, at this state, water is boiling. But if water is boiling at this stage, right? But if you keep heating it and all the water has been changed into vapors, then the temperature will start rising up again. But at this point, there is no water. There's only gas phase. Okay, only gas, only vapors, right? So what happens at this point is that you keep heating, the gas particles, the heat energy would increase the kinetic energy of gas particles or the vapors. Okay, the heat energy increase kinetic energy of gas particles. Right? So the whole idea here is that when you heat it and the temperature is changing, okay, within the same physical state. But when this physical state starts changing, the moment the one physical state starts changing into another one, there is an equilibrium, okay? And if you keep heating it, the temperature would not change until the whole physical state have been changed, right? So the conclusion you can make here, is that during physical state change, these are physical states, solid, liquid, gas, state change, there would be no temperature changes. Okay, so that's what you have to keep in mind, right? So at this point, there's melting going on. If you remove energy or if you cool it down, it would go into solid. If you keep heating it, it would change into liquid. But until all of it changes into liquid, the temperature would not start rising up again. And at this point, what happens is that the water is boiling, and until all the water has been transformed or vaporized into gas phase, the temperature would not start rising up again. Okay, so that's the heating curve, right? Now let's talk about the cooling curve. All right, so that would be the reverse. We would use the same example of water. All right, let me draw a similar graph here. Okay, so what happens is that maybe you already have vapors, okay, gaseous form, right? So what's a cooling curve? I think I already explained this. The cooling curve shows how the temperature would change or how the physical state of a matter would change when you cool it down from gas to liquid to solid, right? So let's say we have a gas, right? Let's say we have water vapors around about like 50 degrees Celsius. You start cooling it down. So temperature would keep decreasing until you reach 100 degrees Celsius. So here you have gas, which is like vapors, right? So once it reaches 100 degrees Celsius and you keep cooling it down, right? The temperature would not change. It will become kind of like constant. Keep cooling it down, the temperature will not change until all the gas have been changed into liquid form, right? So at this phase, you have the boiling point of water, okay? So it's like 100 degrees Celsius, which is like the boiling point of water, okay? So if you further keep cooling it down, then all of it change into liquid, then the temperature start dropping again until it gets to 0. At this point, it's liquid, which is basically water, right? Then at 0, it would start forming ice, and it would keep, or it would stay at that temperature until all of the water has been changed into ice. Okay, so this is ice. Okay, at 0 degrees Celsius. The temperature will start dropping below 0 only when all the water has been changed to ice. All right, so what's going on here? So at this stage, when it's gas and you are cooling it down and its temperature is dropping, okay, as the gas cools, the kinetic energy of particles drops. It decreases. So the particle moves less and less quickly. Okay? Particles move less quickly or less rapidly. Their movement slows down due to less and less energy. When you're cooling it down, you're decreasing energy. Okay? So at 100, the particles would not have enough energy to collide rapidly. All right? So particles have less energy or less kinetic energy. Kinetic energy is due to movement. So when they collide, instead of bouncing back, they would stay there, right? So when they collide, when particles collide, they stay there. And they form some kind of attractive force, okay? So at this point, they would condense into liquid. Instead of running away, moving away, they would try to stay close to each other, right? And at the solid phase, what happens is that liquid was already moving very slowly. Liquid particles move even more slowly. All right? And there would be like stronger attractive forces holding them together, which would make a lattice. So because the particles are unable to move freely now, they don't have enough energy to move freely, don't have enough energy, enough kinetic energy to move freely. So what happens? If they cannot move freely, they don't have enough energy, so they would like to settle down, form a regular arrangement. Okay? So they would make a lattice. So that's the description here of the cooling curve, right? You can say in the gas particle, like here, if you try to draw it, it would be like this. Right? So let's see. So particles are far apart from each other. Okay? Let's use particles are far apart from each other. Okay? But in the liquid phase, right, particles are quite close to each other. They are still moving, but very slowly. All right? And in the solid phase, in the ice solid phase, all right, what happens is that here you have solid, and in the solid phase, the particles would be very close to each other, right? Like this. Probably they would be regularly arranged if it's a crystal like ice. Okay? So it's all about energy, right? If you have a gas or vapors, you're cooling it down, you are removing energy. They cannot move freely now, at least not as much as they were moving previously. So they would move a little bit as in the form of liquids. If you further keep it cooling down, keep removing the energy, the kinetic energy decreases, the particles cannot move freely at all. They would like to settle down. They would come closer to each other. Stronger forces would like to hold those particles together, forming a regular arrangement in the form of solids. Okay? So that's all about heating and cooling curve. The main conclusion, I have written it here. So when you cool down a gas, it would start boiling first. It would become a boiling liquid first. If you keep cooling it down, then it would become a liquid later on, right? The point here is, what if the heating and cooling curve we talked about, this would happen with every substance, with every metal. Let's say if you have iron, is in the solid form, you start heating it, there would come a time when it would start melting and its temperature would stop increasing until the whatever amount of iron you have would have completely melted. And if you keep heating it up, then its temperature would start increasing further until it reaches the boiling point, and then that metal would start boiling. Okay? If you keep heating it further and the temperature the temperature would remain constant until all of that metal would have been changed into gaseous state, and then the temperature would start rising up again. Okay? Obviously, for metal like iron, you would require very extremely high temperature. Okay? Remember that. But this would only happen if we have a pure substance. What if we don't have a pure substance, right? What if substance is not pure? Remember, pure substances usually have a fixed melting and boiling point. Okay? Pure substances usually, not always, usually have a fixed melting point and boiling point. If you add impurities, the impure substances have variable, okay, melting point and boiling point. Let me give you an example. If you have like 3 glasses filled with water and it's pure water, all of them would have 0 degree Celsius, 0 degree centigrade or 0 degree Celsius as melting point and 100 degrees Celsius as boiling point. Now, if you add half a teaspoon of sodium chloride salt in glass A, 1 teaspoon of sodium chloride salt in glass B, and 2 teaspoon of sodium chloride in glass C. So now all 3 of those are salt solution, sodium chloride solution, but with different amount of sodium chloride, or you can say impurities added in them. Now although it's an aqueous solution, although water molecules are still there, but because of the attraction of water molecule with sodium and chloride ions, the boiling point of water would change. Now these are solutions, impure substances. Their boiling point would not be 100 degrees Celsius, it would be slightly above 100 degrees Celsius. So the boiling point would change. And because 3 solutions have different amounts of salts in them, their boiling point would also be slightly different. Okay? I hope that makes sense. Impure substances, depending upon what type of impure substance is that, okay? Impure substances would have different melting point and boiling point depending upon the nature and quantity of impurities added. Okay, what type of impurities are there and how much is the quantity of those impurities, right? And that would determine the forces of attraction. So if forces changes, melting point and boiling point changes. Alright? So in conclusion, this means that the melting point and boiling point can also be used as a check. Melting point and boiling point of a substance can be used as a test or a check if, or you can say whether a substance is pure or not. Or not. So if you have water and it boils exactly at 100 degrees Celsius, not 101, not 102, or not 100.1 or 100.5, no, exactly at 100, then you can say it is pure water. If it does not boil at 100 and boils above 100, like 102, 101, 103, then you can say it is not pure water. There are some substances in it. All right. So that's all about heating curve and cooling curve. Right. Let me know if you have any questions. In the next lesson, I will try to answer all the exercise related questions. This video is already almost like 30 minutes. So far, if you have any queries or any suggestions, let me know in the comments, or you can email me. Right? Take care. See you in the next lesson.